What if the celestial body known as 3I Atlas proves to be a black swan event, a cosmic anomaly that reshapes the course of history? Initially, it was dismissed as merely another interstellar wanderer, a frigid remnant from the void, drifting silently past our sun, leaving behind only data and cosmic debris. However, it failed to depart. Instead, it began to accelerate, not erratically, but with apparent intent. Its velocity shifted, its luminosity pulsed, as if guided by an unseen force. This is where our mathematical models faltered, the equations collapsed. What was once predictable became unfathomable. Astronomers label it an anomaly. But what if it signifies something more profound? What if this represents a one-in-a-billion occurrence, the kind that necessitates a fundamental reevaluation of our understanding of gravity, time, and indeed, chance itself? Remain vigilant, for tonight you will comprehend why an event that might never again grace our planet's existence could be unfolding right now. If this enigma continues to captivate you as it has me, please ensure you click like and subscribe to avoid missing any updates as this unfolds in real time. Share your thoughts in the comments. Where are you watching from? What time is it where you are? And what is your perspective on this emerging possibility? Furthermore, if you wish to support the growth of this community, kindly share this video on X, Facebook, Reddit, or even within your personal group chats. It is your engagement that enables us to continue pursuing stories of this nature. Therefore, thank you for your unwavering support. Part 1. The latest breaking anomalies. Envision this: telescopes swiveling in perfect synchronization across continents, trajectory plots flickering on screens within dimly lit control rooms, a sudden eruption of water vapor emanating from a frozen traveler millions of miles from the sun, headlines flashing across news feeds, alien technology, unexpected acceleration, something unprecedented. This is not the realm of science fiction. It is happening now, and it bears a designation, 3I Atlas, an interstellar comet identified in July 2025, which was anticipated to behave like any other collection of ice and rock we have previously catalogued. Predictable, quantifiable, safe. Yet, 3I Atlas defies expectations, and the deeper we scrutinize, the more perplexing it becomes. When astronomers first detected this visitor from beyond our solar system, they presumed it would follow the established pattern observed with its predecessor, Oumuamua. They believed they understood what to anticipate: outgassing, an increase in brightness as it neared the sun, a trajectory subtly altered by jets of sublimating ice. Nothing alarming, nothing to cause sleepless nights. However, within weeks of its discovery, the collected data began to deviate from the projected outcomes. And now, months later, we are confronted with a phenomenon that defies logical explanation. Allow me to present a specific detail that should send shivers down your spine. This comet is expelling water at an astonishing rate, akin to a fire hose. Crucially, this is occurring far from the sun, the region where frozen volatiles are typically expected to vaporize. Instead, it's happening at a distance of approximately 2.9 astronomical units from the sun. That is nearly 3 times the distance between Earth and our star. At such a remove, most comets are quiescent, dormant, frozen solid. But 3I Atlas is remarkably active, exhibiting violent activity, and its cause remains a mystery to all. The James Webb Space Telescope turned its infrared sensors towards this object and detected an even more curious characteristic. The coma, the luminous envelope of gas and dust surrounding the nucleus, is predominantly composed of carbon dioxide, not water. Furthermore, the ratio of carbon dioxide to water is approximately 8:1. This represents one of the highest carbon dioxide to water ratios ever observed in a comet. Indeed, in the entire history of cometary science. Consider this: we have meticulously studied hundreds of comets. We have analyzed their chemical compositions and developed numerous models. And then this entity arrives from interstellar space and shatters all established patterns. Therefore, the central enigma lies here. If this is a comet, a natural celestial body composed of ice and rock, why is it exhibiting such intense activity so far from the sun? Why is its chemical makeup so extreme? And if its nature is not entirely natural, if there exists even the slimmest possibility of it being something else, then what could it be? A select group of astronomers have begun to employ a term more commonly associated with financial markets and epidemiological studies: black swan. This refers to an event of such extreme rarity and unpredictability that it fundamentally alters the established rules only after its occurrence. Now I understand your thoughts. Comets are known for their peculiarities, and space is replete with outliers. However, consider this. Avi Loeb, an astrophysicist and the same scientist who posited that Oumuamua might be an artificial construct, has highlighted that 3I Atlas exhibits non-gravitational acceleration anomalies that do not align with conventional models. When a comet releases gas, these jets exert a force that subtly alters its trajectory. This is a normal, expected phenomenon. However, 3I Atlas is not accelerating as anticipated. Alternatively, it might be accelerating, but the observed forces do not correlate with the measured outgassing rates. In either scenario, something is amiss. And when fundamental principles of physics fail to reconcile, one must begin to pose uncomfortable questions. Let me illustrate its orbital path. This object is traversing a hyperbolic trajectory. This signifies that it originated from interstellar space and will permanently depart our solar system. It is moving in a retrograde direction, meaning it orbits the sun in the opposite orientation to the planets. Its inclination relative to the ecliptic, the plane in which most planets orbit, is approximately 5 degrees. While this may not sound significant, statistically it is unusual. Most interstellar objects are expected to arrive from random angles. Yet, this one entered our system with an alignment almost parallel to our planetary disk, as if it had a specific destination in mind. Its perihelion, the point of closest approach to the Sun, occurred on October 29th, 2025, mere days ago. At this very moment, as you are hearing this, 3I Atlas is circling the Sun and commencing its outward journey, and scientists are urgently attempting to collect every available piece of data before it fades into the cosmic background. However, here is the question that should occupy your thoughts tonight. Could this object initiate a chain reaction of surprises? Could it already be challenging our assumptions about what is possible? Could it represent the first domino in a sequence we have yet to conceive? Because if 3I Atlas is indeed a black swan event, then by its very definition, we will only recognize its significance in retrospect, after its repercussions have manifested. Over the ensuing 2 hours, we will endeavor to determine whether 3I Atlas is simply an exotic entity, a statistical anomaly within an infinitely vast universe, or whether it is subtly rewriting the laws of space. We will examine 8 distinct scenarios, ranging from the plausible to the highly speculative. Some of these scenarios are grounded in established principles of orbital mechanics and observational astronomy. Others venture into territories that may elicit skepticism from the uninitiated, but that is precisely the nature of such events. A black swan event is not intended to be obvious. It is meant to remain unseen until the precise moment it irrevocably alters reality. We will investigate orbital perturbations that could trigger cascading effects decades from now. We will consider fragmentation events that might introduce future hazards. We will ponder whether this comet could interact with the Sun in ways we have never witnessed. We will explore the potential for artificial signals embedded within the background noise. We will examine atmospheric anomalies, cascades of disclosure, psychological shock waves, and even glitches in reality itself. moments when the instrumentation might reveal fissures in our comprehension of time and space. And here lies an unsettling truth. We may already be enveloped within the Black Swan event. We might be observing its unfolding in real time, misinterpreting it as mere curiosity rather than a potential catastrophe. For this is how such events operate. Their true meaning becomes apparent only in hindsight, after the fundamental paradigm has shifted, after the rules have been rewritten, after it is far too late to prepare. Therefore, let us commence. Let us peel back the layers. Let us scrutinize the data, the speculation, the apprehension, and the wonder. Let us pose the question that few dare to voice aloud. What if 3i Atlas is not merely passing through? What if it signifies the genesis of something we are currently incapable of naming? Part 2. Observed deviations from expectation. Before we delve into the anomalies, it is imperative that we establish a baseline. We must comprehend what constitutes normal behavior, as the only means to identify a deviation is to understand the standard from which it departs. And in the case of interstellar comets, we possess a reasonably clear understanding of what to anticipate, or at least we believed we did. As a comet approaches the sun, solar radiation warms its surface. The ice then undergoes sublimation, transitioning directly from a solid state to a gaseous one. This gas escapes through fissures and vents within the nucleus, carrying dust particles along with it. This process is responsible for the formation of the coma, the luminescent atmosphere, and occasionally a tail extending millions of miles behind the comet. The jets of gas also function as minute thrusters, imparting a slight deviation to the comet's gravitational trajectory. This phenomenon is termed non-gravitational acceleration, and it is a predictable outcome. Based on the comet's distance from the Sun, its dimensions, and its composition, astronomers are able to calculate the extent to which it should deviate from a purely gravitational path. Comets also exhibit an increase in brightness as they approach the Sun. This luminosity change follows a power law relationship. The closer they get, the more active they become and the brighter they appear. Scientists employ a metric known as the heliocentric distance exponent to characterize this correlation. For the majority of comets, this exponent falls within a specific range. If it deviates significantly above or below this range, it suggests an unusual composition or behavior. This, then, is our benchmark. Outgassing intensifies closer to the Sun. Brightness follows predictable curves. Non-gravitational forces align with outgassing rates. Photometric behavior corresponds with distance. This is straightforward, verifiable, and reliable. Now let us address 3i Atlas. At an approximate distance of 2.9 astronomical units from the Sun, it was already releasing water at rates typically observed much closer to the solar body. Imagine activating a faucet in sub-zero temperatures and observing water flow nonetheless. This is essentially what is occurring here. At such a distance, most comets are inactive. Their surfaces are too cold to facilitate significant sublimation. However, this comet appears indifferent to our established models. The James Webb Space Telescope analyzed the composition of its coma and discovered something extraordinary. Carbon dioxide is the dominant constituent. The ratio of carbon dioxide to water stands at approximately 8:1. To provide context, most comets within our solar system exhibit ratios closer to 1:10 or 1:20. Water is typically the primary volatile substance, but not in this instance. Here, carbon dioxide reigns supreme, and its dominance is inexplicable. Is the nucleus unusually enriched with carbon dioxide ice? Did it form in a colder, more carbon-rich region of its parent star system, or is some other mechanism releasing the carbon dioxide in a manner we do not yet comprehend? Dust production presents another peculiarity. Observations from the Nordic Optical Telescope quantified the scaling of dust production with distance. The power law index derived from these measurements was approximately 3.8, with a margin of error of 0.3. This figure indicates the comet's sensitivity to solar heating. A higher index signifies rapid changes in activity, while a lower index denotes gradual alterations. 3I Atlas falls within a recognized range, yet it is situated at the upper end of this spectrum. It is reacting robustly to solar radiation, more so than would be expected for an object of its presumed composition. Furthermore, there is the matter of polarimetry. When sunlight disperses off dust particles within the coma, it becomes polarized. The degree and angle of polarization are contingent upon the size, shape, and composition of these dust grains. Astronomers who observed 3I Atlas documented what they termed extreme negative polarization. This is a technical descriptor indicating that the polarization behavior deviates from that of known solar system comets. The phase angle dependence, which describes how polarization shifts with changes in the viewing angle, is unusual and anomalous. Now let us discuss its trajectory. 3I Atlas is following a hyperbolic orbit with an eccentricity exceeding 1. This means it is not gravitationally bound to the Sun. It will escape our solar system. Its inclination relative to the ecliptic is approximately 5 degrees, and it is moving in a retrograde fashion. This particular combination of orbital characteristics is statistically infrequent. Most interstellar objects are anticipated to arrive from random directions. The fact that this object entered our system with an alignment so nearly parallel to the plane of the planets is, perhaps, a coincidence. However, in astronomy, coincidences often mask deeper truths. Perihelion occurred on October 29, 2025. Currently, the comet is moving away from the Sun. On October 3, 2025, it passed within approximately 0.19 astronomical units of Mars. This is a close encounter, closer than many instances involving near-Earth asteroids. On November 3rd, it will pass within 0.65 astronomical units of Venus. And in March 2026, it will approach within 0.36 astronomical units of Jupiter. These close proximity events do not pose a risk of collision, but they do raise questions regarding gravitational interactions. Could this object perturb the orbits of smaller celestial bodies? Could it subtly alter the path of an asteroid? We will revisit this question later. Here is where the situation becomes truly perplexing. Despite significant outgassing, despite the abundance of water and carbon dioxide being released from its surface, 3I Atlas does not exhibit the anticipated non-gravitational acceleration, or, at the very least, the acceleration is considerably less than theoretical models predict. Avi Loeb has pointed out that this suggests the nucleus must be either exceptionally massive or remarkably dense. If the jets are expelling material against a substantial mass, the resulting acceleration will be minimal. Conversely, if the nucleus is small and the outgassing is weak, whence does all this water originate? The figures do not reconcile, the forces do not balance. There is a missing element in the equation. Estimates of its size vary considerably. Depending on assumptions regarding reflectivity and composition, the nucleus could range in diameter from 0.32 kilometers to 5.6 kilometers. This represents a substantial degree of uncertainty, and this uncertainty propagates through every calculation we perform. If the nucleus is small, the outgassing rates are extraordinary. If it is large, the absence of significant acceleration is equally extraordinary. In either scenario, we encounter a degree of absurdity. Therefore, what are the implications? If outgassing is expected to alter the object's trajectory, yet it deviates minimally, we are presented with several possibilities. Perhaps the jets are perfectly symmetrical, neutralizing each other's effect. Perhaps the nucleus is rotating in such a manner that the thrust is distributed uniformly. It is also conceivable that the material being ejected possesses such low velocity that it imparts negligible momentum. Or just perhaps the nucleus is denser than any object we have previously encountered. Denser than rock, denser than iron, dense enough to provoke questions about its fundamental composition. And this leads us to the uncomfortable inquiry. Is this merely an unusual comet? Or is it the initial indication of something far more unpredictable? Because if we are unable to explain its behavior using standard models, then our models are incomplete. And if our models are incomplete, what other phenomena might we have overlooked? Part 3. Media and Community Reaction. Speculative Framing. The astronomical community is experiencing a division of opinion. On one side stand the cautious establishment figures, scientists who have dedicated their careers to the study of comets, individuals who place their trust in empirical data, who await peer review, and who actively resist sensationalism. On the other side are the provocateurs, researchers who are willing to entertain hypotheses with low probabilities but high potential impacts, individuals who believe the universe may still hold surprising revelations. And in the space between these two poles, we find the media, amplifying both perspectives, at times with responsibility, and at others with recklessness. Tom Statatler, NASA's lead scientist for small bodies in the solar system, has publicly stated that 3I Atlas is behaving like a comet. He has emphasized that the overwhelming body of evidence points towards a natural celestial object. Water outgassing, dust production, and photometric behavior consistent with sublimation. These are all characteristic hallmarks of a comet. He asserts there is nothing to suggest any artificial or exotic nature. It is simply a piece of ice from another star system, behaving as such objects typically do. However, there is also Avi Loeb, the Harvard astronomer who gained widespread recognition after proposing that Oumuamua might be a light sail. Loeb has been vocal concerning 3I Atlas. He has drawn attention to the anomalous acceleration patterns. He has questioned the underlying assumptions of our scientific models, and he has urged the scientific community not to dismiss low-probability hypotheses without thorough investigation. He is not positing extraterrestrial origins. Rather, he is advocating for exploration, as he believes that without investigation, knowledge remains elusive. And then there is the media. Tabloid publications have featured headlines speculating about disguised hostile alien technology. Major news outlets have embraced the black swan framing, characterizing it as a rare object with the potential to fundamentally alter our understanding. The Guardian has published articles that aim to balance scientific caution with public curiosity. Live Science has explored the possibility of artificial origins, presenting it as unlikely but not entirely inconceivable. Scientific American has covered Loeb's remarks, highlighting the importance of empirically ruling out exotic explanations rather than relying on assumptions. The Times of India has referred to 3I Atlas as a rare black swan object and mentioned an international observational campaign coordinated by the International Asteroid Warning Network, IAWN, a consortium of telescopes and space agencies dedicated to the detection and tracking of near-Earth objects. The fact that IAWN is involved suggests that this object is being taken seriously, not as an imminent threat, but as something warranting close observation. So, why would scientists even entertain narratives of alien technology? Why risk their credibility by engaging with speculation? The reason lies in the asymmetry of the risks involved. If one ignores a low-probability event that subsequently proves to be real, the consequences can be catastrophic. Conversely, if one investigates and discovers nothing, the only cost incurred is time and resources. This principle mirrors Pascal's wager as applied to astronomical inquiry. The potential cost of being wrong far outweighs the risk of appearing foolish. However, a more disquieting aspect of this framing exists. Speculation can foster fear. It attracts conspiracy theorists. It blurs the distinction between responsible scientific inquiry and irresponsible fear-mongering. When mainstream media outlets begin to employ phrases such as alien tech and black swan, they are not merely reporting information, they are actively shaping public perception. They are influencing how the public, and indeed policymakers, react to uncertainty. Consider this scenario. What if 3I Atlas is entirely benign? What if it is simply a comet with an unusual but ultimately explainable chemical composition? However, due to the prevailing speculation and framing, resources might be diverted. Telescopes could be redirected from other crucial targets towards this object. Debates regarding planetary defense budgets might arise. International collaborations could form around what is ultimately a non-threat. And all of this could transpire because we failed to differentiate between prudent caution and unwarranted paranoia. On the other hand, what if the speculation is indeed justified? What if there exists even a 1% probability that this object represents something unprecedented? In such a case, neglecting to investigate would be a dereliction of duty, both dangerous and a failure of imagination. For the fundamental characteristic of a black swan event is its unpredictability. One cannot prepare for it by adhering to established protocols. It necessitates a willingness to entertain the seemingly impossible. This inherent tension influences funding decisions, the allocation of telescope observation time, and the seriousness with which space agencies approach follow-up studies. An object labeled a mere curiosity might receive minimal attention. However, if it is characterized as a potential black swan, suddenly everyone expresses interest. Careers can be forged or broken, depending on whether the heightened attention proves to be warranted. There is also a psychological dimension to consider. Why does this particular phenomenon evoke such intense fascination? Why does the concept of an interstellar visitor elicit both awe and apprehension? Perhaps it serves as a stark reminder of our cosmic insignificance, the fragility of our understanding, and the vast expanse of the unknown that remains within the universe. Or perhaps, deep down, we harbor a longing for something to disrupt the mundane, a desire for proof that we are not alone, or conversely, evidence that the cosmos is far stranger than we have ever imagined. The concept of a black swan event transcends scientific discourse. It is a cultural phenomenon. It pertains to our response when confronted with the unknown. Do we dismiss it as mere noise? Do we investigate it as a significant signal? Do we allow fear to guide us, or curiosity? Because once a black swan event transpires, once the established paradigm shifts, there is no turning back. It cannot be unseen. Its implications cannot be unlearned. The world is irrevocably different in its aftermath. Therefore, the critical question is this: are we elevating 3I Atlas into something it is not through excessive hype? Or are we finally acknowledging the genuine possibility that space can still offer us profound surprises? Because the answer to this question will ultimately dictate our approach to the next anomaly, and the one that follows, and the one after that. But to determine if this phenomenon is mere excitement or a genuine danger, we must first establish what constitutes a cosmic black swan event. Without a clear framework or established criteria, we are left to mere speculation, and such conjecture is insufficient, especially given the potentially significant implications. Part 4 will focus on defining what a space-based black swan event might entail. The concept of a black swan originates from the philosopher and statistician Nassim Taleb, who used it to describe events that are exceptionally rare, inherently unpredictable, and possess monumental consequences. These are occurrences that, in hindsight, appear obvious but were completely unforeseen beforehand. A prime illustration of this is the 2008 financial collapse. Experts had assured everyone of the system's stability, the diversification of risks, and manageable leverage, only for the entire structure to crumble. Afterward, the warning signs became apparent to all. However, prior to the collapse, these same indicators were dismissed as inconsequential noise. Taleb posited that black swan events share three fundamental characteristics. Firstly, they lie beyond the scope of normal expectations, with no prior occurrences convincingly suggesting their possibility. Secondly, they carry an extreme impact, capable of reshaping industries, societies, or even fundamental worldviews. Thirdly, despite their unpredictability, human nature compels us to retroactively devise explanations, making them seem logical and foreseeable. We contrive causality, asserting that we should have anticipated them, when in reality, we could not have. So, how does this translate to the realm of astronomy? What would qualify as a black swan in the context of space? Perhaps a comet that initiates a chain reaction of orbital disturbances, or an object that reveals entirely new physics. It could be a signal confirming extraterrestrial intelligence, or a disturbance so subtle that its effects only become evident decades later. Let me propose a set of working criteria. A space black swan event must exhibit at least three of the following attributes. First, it must be unpredictable beyond the capabilities of current models, not merely unusual or infrequent, but genuinely outside the parameter space of existing theories. Second, it must carry a high potential impact on planetary safety, scientific understanding, detection systems, or humanity's perception of its place in the cosmos. Third, it must result in irreversible consequences, such as orbital shifts persisting for millennia, irreparable loss of data integrity, or new scientific understandings that render existing textbooks obsolete. Fourth, there must be evidence of intentionality or physical anomalies that transcend natural randomness, such as a signal inexplicable by known astrophysical processes, a trajectory correction defying inertia, or a temporal coincidence so precise as to be dismissible. Now, let us apply these criteria to Comet 3I Atlas. Does it already meet any of them? Well, its unpredictability lies in its behavior not perfectly aligning with existing models. However, the question remains whether it truly exceeds current models or merely stretches their limits, a point of contention. Does it possess a high potential impact? Scientifically, yes, as it challenges our assumptions, but practically, it poses no direct threat to Earth. Does it exhibit irreversible consequences? Not yet. And is there evidence of intentionality? None that we have detected so far. Therefore, by these specific criteria, 3I Atlas does not qualify as a black swan, at least not at this juncture. However, it has the potential to become one. If it behaves unexpectedly, fragments in an unusual manner, perturbs another celestial body, or if a detectable signal emerges, or if any of a dozen improbable scenarios unfold, then retrospectively, we will acknowledge it as a black swan all along. And therein lies the paradox. A black swan event cannot be identified before it occurs. We can only prepare for the possibility, design systems resilient enough to absorb surprises, and foster a mindset that treats the improbable as worthy of investigation. So, what are the specific scenarios? How could 3I Atlas evolve into a black swan? I have identified 8 distinct possibilities. Some are rooted in physics, others are speculative, and a few verge on the metaphysical. Yet, each represents a unique form of potential catastrophe, a different trajectory from curiosity to crisis. The first scenario I term orbital domino. A minor gravitational influence initiates a cascade of orbital alterations for other objects. Perhaps 3I Atlas nudges an asteroid as it passes Mars, causing a slight orbital shift. Over decades, this alteration compounds, and eventually, the asteroid's path intersects with Earth's, a development we entirely missed because we failed to track the initial perturbation. The second scenario is a fragmentation event. The comet disassembles in an atypical fashion. Possibly one fragment displays directed propulsion, or it decelerates contrary to the expected direction of outgassing. It might exhibit characteristics suggesting internal structure, propulsion, or something we cannot currently comprehend. The third scenario involves solar disruption. A solar event, such as a coronal mass ejection or a flare, coincides with the comet's closest approach to the Sun in a remarkably precise manner. There could be a reciprocal effect. Perhaps the comet triggers the solar event, or the timing is simply too coincidental to be random, leading to satellite failures and communication blackouts, accompanied by auroras in unexpected locations. The fourth scenario is an artificial signal. Telescopes might detect a narrow-band pulse, too fleeting to confirm and too weak to repeat, buried within background noise until a specific algorithm is applied. The critical question then becomes, should we announce this discovery, pursue further investigation, or suppress it due to the potentially destabilizing implications? The fifth scenario is an atmospheric anomaly. The comet's passage might trigger or coincide with unforeseen disturbances in Earth's upper atmosphere, such as ionospheric spikes, GPS signal delays, or off-season auroras. Similar effects could be detected by Mars orbiters, transient, subtle, yet measurable. The sixth scenario is a disclosure cascade. Unforeseen leaks, coordinated official statements, or data releases timed with the object's flyby could occur. This might be benign, a standard scientific coordination, or it could signify the commencement of a controlled information release, a gradual disclosure to prepare the public for a larger revelation. The seventh scenario is a psychological singularity. Widespread public attention could incite a social cascade of synchronized events, heightened anxiety, and a collective belief that a significant event is imminent. Consequently, due to this widespread belief, decisions will be made, policies will shift, funding will be allocated, and careers will pivot, rendering the object significant not for what it is, but for what we perceive it to be. The eighth scenario is a reality glitch. This is an extremely speculative proposition. Slight desynchronization of instrumentation, anomalies in pulsar timing, spacecraft telemetry discrepancies, or atomic clock drift, all aligning with the comet's transit, as if the object is somehow distorting space-time itself, or revealing a fundamental flaw in our understanding of time. Each of these scenarios prompts a different inquiry. Could a fragment alter an asteroid's trajectory decades from now? Is it conceivable that we have already recorded a signal that vanished before we recognized its significance? Can a comet interact with the sun in ways we have not yet witnessed? Can public perception manifest as a self-fulfilling prophecy? Some of these are grounded in scientific principles. Orbital perturbations and fragmentation are well-established phenomena. Others possess a cinematic, almost paranoid quality. However, that is precisely the nature of a black swan. It is not the most probable outcome, but rather the overlooked one, the scenario dismissed as too improbable until it materializes. In the subsequent sections, we will delve into each scenario with greater detail, examining which remain plausible given current data, which can be definitively ruled out, which are inherently unknowable, and which might already be in progress without our awareness. Because if even one of these scenarios proves to be real, our comprehension of the universe will be irrevocably altered. Part 5 offers a preview of these 8 extraordinary possibilities. Let us examine these scenarios sequentially, not with exhaustive detail at this stage, but sufficiently to grasp their essence and appreciate the weight of their potential implications. Each scenario represents a distinct manner in which the cosmos could surprise us, and each carries consequences for which we are unprepared. Scenario 1. Orbital Domino. Envision 3I Atlas approaching Mars on October 3, 2025. It does not collide with anything, but its gravitational influence exerts a minute tug on a small asteroid, altering its velocity by a fraction of a meter per second. This might seem insignificant at present, but orbital paths are inherently sensitive systems where small deviations amplify over time. A decade later, the asteroid's trajectory has shifted. 20 years on, it crosses another orbit. 30 years hence, it is on a direct collision course with Earth. A catastrophic outcome we failed to foresee because we did not track the initial perturbation. Could 3I Atlas initiate such a chain reaction, nudging something into a future threat? The mathematics suggest it is possible, however improbable. Scenario 2. Fragmentation event. Comets commonly fragment due to thermal stress, rotational forces, or inherent structural weaknesses. However, what if a fragment behaves abnormally? What if it decelerates when it should accelerate, or changes direction against the propellant forces of the outgassing jets? Imagine astronomers detecting a secondary burst of brightness weeks after perihelion, assuming it's a fragment. Yet, upon calculating its trajectory, the numbers do not align. The fragment's momentum contradicts the expected ejection velocity, implying movement as if propelled or steered. Is this naturally feasible? Perhaps, but it would necessitate internal structures, cavities, pressure differentials, or phenomena yet unknown to us. Scenario 3. Solar disruption. The Sun is an active star with coronal mass ejections and solar flares occurring regularly. But what if such an event coincides precisely with the comet's perihelion passage? What if the timing is extraordinarily precise, and the comet's approach aligns with a massive CME directed squarely at Earth? Satellites could fail, power grids might fluctuate, and auroras could appear at the equator, leaving scientists to debate whether it is coincidence or causation. Could a comet trigger a solar event? Mainstream astrophysics suggests this is unlikely, given the comet's minuscule size relative to the Sun's immense mass. However, what if there is a reciprocal interaction? What if the comet's ionized coma couples with the Sun's magnetic field in an unforeseen manner? Or if our understanding of critical thresholds is flawed? Scenario 4. Artificial signal. Radio telescopes continuously scan the cosmos, collecting vast amounts of data, filtering out noise and searching for patterns. But what if a signal has already been recorded and missed? What if 3I Atlas emitted a brief pulse during its perihelion? What if it was positioned behind the Sun, precluding immediate follow-up? What if the signal was dismissed as mere interference? Picture a researcher years from now running archival data through a novel algorithm and discovering something extraordinary. A narrow band emission, structured and non-random, originating from that specific moment and object. Would we announce it? Would we accept its implications? Or would we suppress it due to the profound and potentially dangerous ramifications? Scenario 5. Atmospheric anomaly. Earth's ionosphere is susceptible to solar wind and cosmic rays, but it also reacts to charged particles emanating from comets. What if 3I Atlas's coma interacts with Earth's magnetosphere? What if GPS signals exhibit unusual delays, or ionospheric monitoring stations detect significant spikes in ion density? What if Mars orbiters register transient auroras during the October 3rd close approach? These effects might be subtle and easily dismissed. However, if multiple independent instruments detect anomalies within the same temporal window, coincidence transitions to correlation, and correlation necessitates an explanation. Scenario 6. Disclosure Cascade. The International Asteroid Warning Network publicly coordinated an observation campaign for 3I Atlas. This is common knowledge. But what if there were other unannounced meetings? What if space agencies secretly shared data? What if previously identified anomalies were re-examined and re-released during this period, not due to conspiracy, but because the object warranted a more rigorous look at historical data? And what if this re-examination uncovered discrepancies? Timing residuals in spacecraft telemetry, unexplained deviations in the trajectories of other missions. Nothing definitive, but enough to spark curiosity and initiate a cascade of questions. Scenario 7. Psychological Singularity. This scenario is challenging to quantify, as it is less about physics and more about collective perception. What if a sufficient number of individuals come to believe that a significant event is imminent? What if social media amplifies speculation to an extreme degree? What if policymakers begin to treat the speculation with seriousness, leading to emergency meetings and shifts in funding priorities? The object's significance would then derive not from its actual properties or actions, but from our collective belief in its potential. In a peculiar fashion, our belief would reshape reality, not the object's physical reality, but our societal reality. Decisions would be made, careers would pivot, and history would be altered, all because we were unable to distinguish between genuine signals and mere noise. Scenario 8. Reality Glitch. This is the most audacious scenario, venturing into territory few scientists are willing to explore. What if multiple independent sensors recorded timing anomalies during the comet's passage? Pulsar timing residuals, atomic clock drift, spacecraft telemetry delays, all minute, all within acceptable error margins, yet all coinciding precisely with 3I Atlas's perihelion. What would be the implications? Could ionized dust particles distort signal propagation? Could charged particles interfere with time distribution systems? Or could this reveal something more profound? A flaw in our synchronization mechanisms, a distortion in space-time, or evidence that our clocks are not measuring time as we fundamentally understand it? Let us be clear. Most of these scenarios are highly improbable, and some are virtually impossible. However, the focus here is not on probability, but on consequence. A black swan does not announce itself. It lurks in the extremities of statistical distributions, concealed within the noise. It only becomes undeniably apparent after it has transpired. Over the coming segments, we will meticulously examine which of these scenarios possess supporting evidence, which are empirically testable, which remain purely speculative, and which might already be unfolding without our conscious awareness. Because if we find ourselves within a black swan event at this very moment, our only recourse is to observe, and to continue observing until the full picture becomes clear, or until it is regrettably too late. Part 6 will scrutinize scenarios 1 and 2, the orbital domino effect and the fragmentation event. We will commence with the most plausible scenarios, those firmly rooted in established physics, eschewing exotic hypotheses or conspiratorial conjecture. Because if 3I Atlas is destined to surprise us, it is most likely to do so in a manner that is subtle, delayed, and concealed within the intricate mathematics of orbital mechanics. The orbital domino scenario is precisely what keeps planetary defense scientists vigilant, not due to its high likelihood, but because its consequences escalate over time, rendering intervention impossible by the time the problem is recognized. Here is how it operates. 3I Atlas traverses the inner solar system. As it passes by planets and large asteroids, its gravitational field exerts an infinitesimally small tug, a fractional influence negligible in the short term. However, orbital systems are inherently chaotic and highly sensitive to initial conditions. A minuscule alteration in velocity can propagate into a substantial deviation in position over decades. On October 3, 2025, 3I Atlas passed within approximately 0.19 astronomical units of Mars, a distance of roughly 28 million kilometers. For perspective, the Moon is only 384,000 kilometers from Earth. Thus, by astronomical standards, this was a relatively close encounter. Did it perturb any celestial bodies? Almost certainly. Mars possesses two small moons, Phobos and Deimos, whose orbits are already unstable on geological timescales. A passing object could impart a minor nudge. Would we detect this immediately? Likely not. The changes would be subtle, but over years these deviations would accumulate. Furthermore, Mars hosts a population of co-orbital objects, asteroids sharing its orbital path, known as Trojans. These celestial bodies are gravitationally stabilized by Mars, residing at stable Lagrange points. Yet, stability is a relative term. A perturbation could displace one of these asteroids from its Lagrange point, rendering its trajectory unpredictable. It could drift inward toward Earth, outward toward the asteroid belt, or enter a resonant configuration with Jupiter that amplifies its orbital eccentricity. Let us consider the numerical implications. Assuming 3I Atlas possesses a mass of 100 trillion kilograms, equivalent to that of a mountain or a small comet nucleus, its gravitational influence at a distance of 0.22 astronomical units would be extremely minute. However, minute does not equate to zero. Gravitational force diminishes with the square of the distance, but never entirely vanishes. Every object within the solar system exerts a force upon every other object, and these forces are cumulative. Now, consider an asteroid with a semi-major axis of 2 astronomical units, placing it within the main asteroid belt. Its orbital period would be approximately 3 years. If 3I Atlas perturbs its velocity by a mere 1 millimeter per second, this may seem negligible. However, over 10 orbital periods, or 30 years, this 1 millimeter per second translates into a positional change of hundreds of kilometers. And if that asteroid happened to be on a trajectory that could eventually intersect Earth's orbit, those hundreds of kilometers could be the decisive factor between a near miss and a direct impact. Planetary defense networks meticulously track near-Earth asteroids, cataloging their orbits and predicting close approaches. However, they do not track every asteroid. Smaller or dimmer objects often escape detection. Crucially, they do not account for perturbations caused by interstellar visitors, which, until the discovery of Oumuamua, were largely hypothetical. Now, their reality is established, and with it, their potential to perturb orbits. Therefore, the paramount question becomes, could 3I Atlas have nudged a celestial body into a future threat trajectory? The answer is that we do not know. We lack comprehensive orbital data for every minor body in the solar system. We do not possess the computational capacity to model every conceivable perturbation, nor do we have the telescopic coverage to detect subtle changes in trajectories. The vast gaps in our knowledge are precisely where black swan events can lie hidden. Now let us address the fragmentation event scenario. Comets fragment with considerable frequency. It is one of their most common behaviors. Thermal stress induced by solar heating causes the nucleus to fracture. Rotational forces generate centrifugal stresses that pull apart weakly bound material. Sublimation of volatile ice beneath the surface creates internal pressure, expelling fragments. We have observed dozens of cometary fragmentations. Comet Shoemaker-Levy 9 famously disintegrated into numerous pieces before impacting Jupiter in 1994. Comet Schwarzmann-Wachmann 3 has fragmented repeatedly over decades. Therefore, fragmentation itself is not anomalous. However, what if the fragmentation behavior deviates from the norm? What if a fragment does not behave as dictated by physical laws? Imagine this. 3I Atlas is actively outgassing, with jets emanating from its nucleus, imparting momentum. When a fragment breaks away, it should inherit the parent body's velocity, augmented by the ejection velocity from the breakup event. We can calculate the expected outcome, predicting the fragment's brightness, trajectory, and evolution over time. But what if a fragment fails to conform to these predictions? What if its behavior is inexplicable by the action of outgassing jets? That would be highly unusual, though not entirely impossible. It would necessitate the invocation of internal structures, perhaps cavities channeling gas in specific directions, or an asymmetrical tumbling motion generating an off-axis thrust. It might be composed primarily of dust with minimal ice, resulting in weak but present outgassing. Or it could be something else entirely, a mechanism we have yet to understand, a propulsion effect embedded within the physics of cometary activity. Or, in the most extreme interpretation, it might not be entirely natural, with something internal directing its motion. I am not asserting this as probable, but rather stating that if a fragment exhibited such behavior, it would warrant serious consideration. Has 3I Atlas fragmented? As of its perihelion passage on October 29, 2025, there were no confirmed reports of fragmentation. However, this does not preclude the possibility, as comets frequently fragment during or after perihelion when thermal stress is at its peak. Subsequent observations over the ensuing weeks will be critical. Should there be a sudden surge in brightness, the appearance of multiple entities within visual records, or trajectories exhibiting unforeseen deflections, these would constitute telltale indicators. And herein lies the disquieting aspect. If a fragment were to display aberrant conduct, how would we embark upon its scrutiny? Telescopes possess inherent limitations in resolving minute particulars. While spectroscopy can ascertain composition, it falls short of revealing structure. Radar might discern rotational velocities and surface characteristics, but solely if the fragment approaches sufficiently close. Furthermore, if it is receding from the Sun, it is also moving away from Earth. With each passing day, it diminishes in luminosity, rendering observation increasingly arduous. Eventually, it would vanish into the cosmic background radiation, leaving us with scant and incomplete data, a pun indeed, with unverified measurements and unresolved enigmas. Consequently, could a fragment potentially engender future perils? Might it enter an elongated orbital path that would return it centuries hence? Could it subtly alter the orbit of another celestial body? Might it convey vital information concerning the parent body's internal structure, which we would then be forever unable to recover? Affirmative to all these propositions, the process of fragmentation is inherently capricious. It introduces novel variables into an already volatile system, and every new variable represents a potential avenue for unforeseen outcomes. Allow me to present a hypothetical temporal progression. Envision a fragment detaching itself in November 2025. Too dim for immediate detection, it drifts. Over a span of 5 years, its orbital path evolves. By 2030, it intersects the trajectory of a near-Earth asteroid. By 2040, that asteroid's orbit undergoes a minor alteration. By 2060, the asteroid is on a direct collision course with a satellite network, and no one makes the connection back to 3I Atlas because the chain of causation is excessively protracted, excessively indirect, and excessively obscured by extraneous data. This is the domino effect of orbital mechanics, the scenario that haunts the dreams of celestial dynamics experts. For while orbital mechanics is theoretically predictable, it is practically chaotic. Trajectories can be mapped with remarkable accuracy over brief periods. However, over decades, even centuries, infinitesimal uncertainties can escalate into vast divergences, and that which cannot be foreseen cannot be prevented. Thus, what is the pronouncement on these two hypothetical situations? Are they feasible? Yes. Are they probable? No. Do they embody the potential for black swan events? Absolutely, because the repercussions are delayed, the causal links are obscured, and by the time the consequences materialize, the originating event is ancient history. We would possess no means of tracing it back, no way to assert that this occurred due to 3I Atlas. It would simply be perceived as another asteroid, another fragmentation event, another orbital perturbation, lost within the inherent disorder of our solar system. Nevertheless, if we are genuinely committed to planetary defense, if we are earnestly dedicated to long-term survival, we must acknowledge and account for these eventualities. We must track visitors from beyond our solar system, not merely during their transit, but also in their aftermath. We must meticulously model their gravitational impact on smaller celestial bodies. We must diligently monitor for fragmentation events and meticulously characterize any resultant fragments, as the cosmos operates independently of our theoretical constructs and presumptions. It simply proceeds according to its own immutable laws, and we must either adapt to this reality or face the inevitable repercussions. Part 7 addresses Scenarios 3 and 4, Solar Disruption and Artificial Signal. We now venture into territory that renders most scientific minds uneasy, not due to inherent physical impossibility, but rather because it necessitates a confluence of coincidences, temporal alignments, and correlations that, while potentially random, appear remarkably precise. Human beings, it is widely acknowledged, exhibit a pronounced susceptibility to misinterpreting coincidence. We perceive patterns where none exist, infer causation from correlation, and construct narratives that resonate as truthful, even when devoid of factual basis. However, on occasion, coincidences are not mere happenstance. Timing can indeed be paramount, and sometimes the universe presents us with an unexpected challenge that demands thorough investigation. Therefore, let us explore the concept of solar disruption, the notion that 3I Atlas's closest approach to the Sun could coincide with or even precipitate solar activity that impacts Earth. The Sun itself is a chaotic system, its surface a turbulent expanse of convective currents, its magnetic field constantly twisting and intermingling. Every 11 years, its polarity reverses, driving the cyclical solar activity. During periods of solar maximum, sunspots proliferate, coronal mass ejections occur with greater frequency, and solar flares erupt with energies comparable to billions of nuclear detonations. All this activity propels radiation and charged particles outward into space. When a coronal mass ejection strikes Earth, it compresses our magnetosphere, channeling charged particles along magnetic field lines toward the poles. These particles collide with atmospheric atoms, producing auroras. Should the coronal mass ejection be sufficiently powerful, it can induce electrical currents within power grids, leading to the failure of transformers. It can disrupt satellite operations and trigger widespread radio blackouts. The Carrington event of 1859 stands as the most potent solar storm ever documented. Telegraph systems ignited, and auroras were visible even at the equator. A similar event today would incur economic damage potentially amounting to trillions of dollars. Consequently, solar activity is a palpable and potent force, posing significant risks and exhibiting unpredictability on short timescales. While we can forecast the general solar cycle and discern broad trends, precisely predicting the eruption and trajectory of a coronal mass ejection remains elusive due to the inherent chaos within the system. Now, a pertinent question arises. Could a comet interact with the Sun in a manner that either triggers or amplifies solar activity? Mainstream astrophysics posits a negative answer, citing the comet's negligible mass in comparison to the Sun, its insignificant gravitational influence, and its potentially trivial magnetic field. No plausible mechanism exists for a comet to exert influence over the Sun. However, what of secondary effects? Consider the comet's ionized coma, the cloud of ionized gas and dust generated by 3I Atlas's outgassing as it approached perihelion. This cloud possesses electrical conductivity. Could it engage with the Sun's magnetic field? Could it initiate a feedback loop, acting as a catalyst for instabilities already developing within the solar corona? I am not suggesting this is probable, but rather that it is not demonstrably impossible. If solar activity were to surge during the perihelion window, if a major coronal mass ejection were to erupt on October 29th or 30th, and if Earth were to experience unusual auroral displays or satellite disruptions precisely within that time frame, we would be compelled to question whether it was mere coincidence. Let me verify. Were there any significant solar events documented around October 29th, 2025, such as coronal mass ejections, solar flares, or geomagnetic storms? If such events occurred, the timing would be undeniably striking. Conversely, if no such events were recorded, this particular scenario would lose considerable credibility. However, the absence of an event does not render the scenario impossible. It simply indicates it did not transpire on this occasion. For the crucial question is not merely whether it occurred, but whether it could occur, and whether we would recognize it if it did. Now, let us turn our attention to the artificial signal scenario. This is the proposition that causes skeptics to scoff and invites derision, yet it is also the scenario with the most profound implications. For if it proves to be true, if 3I Atlas is something other than a naturally occurring comet, then everything changes. The search for extraterrestrial intelligence, SETI, has been diligently scanning the cosmos for decades. Radio telescopes meticulously listen for narrow-band signals, while optical telescopes search for laser pulses. Sophisticated algorithms sift through vast quantities of data, seeking any discernible patterns. To date, no definitive evidence has been found. The enigmatic "wow" signal of 1977 remains unexplained but unrepeated. Fast radio bursts have subsequently been attributed to astrophysical phenomena, likely originating from magnetars. Every candidate signal has either dissolved into background noise or been accounted for by natural processes. However, here is a critical consideration. SETI operates under the assumption that any signals will be continuous or repeating. A civilization broadcasting intentionally would aim for maximum audibility, transmitting for extended durations, targeting promising stellar systems, and employing frequencies that readily penetrate interstellar dust. These are logical strategies for communication across light years. But what if the intent is not broadcasting, but rather travel? What if the object is a probe, transmitting only during its perihelion passage, utilizing solar conjunction as a means of concealment? What if its signal is deliberately crafted to be ambiguous, weak enough to be dismissed as interference, brief enough to preclude confirmation, yet structured sufficiently to be detected by diligent observers, provided they are actively searching? Imagine 3 Atlas emitting a pulse on October 29th, a narrow-band transmission at 142 GHz, the hydrogen line, a classic SETI frequency, lasting merely 3 seconds. The signal strength barely exceeds the noise floor. Telescopes would record it, but the data would likely be classified as radio frequency interference of human origin, terrestrial, and consequently filtered out by standard algorithms, never to be examined again. Years later, an analyst processing archival data through a new machine learning algorithm might discover it. This algorithm, unburdened by human biases, would merely seek patterns and, in doing so, might identify one, a brief, structured pulse, definitively non-random, originating from the direction of 3I Atlas during its perihelion. By that time, however, the object would have journeyed beyond Jupiter, fading into obscurity, rendering any follow-up or confirmation impossible. Would such a detection be publicly announced? Would it be published, or would it be suppressed? The ramifications are profoundly destabilizing. If it is genuine, if it is artificial, then we are not alone. We have been visited, and we failed to recognize it initially. This leads to uncomfortable questions regarding the number of other signals we might have missed, the number of other visitors we may have overlooked, and the extent of our collective blindness. Conversely, if it is not real, if it is merely noise, then announcing it would incite panic, erode public trust in scientific endeavors, fuel conspiracy theories, and divert valuable resources from legitimate research. Thus, the decision-making process becomes political rather than purely scientific. Do we disseminate the truth and risk societal upheaval, or do we withhold information and face accusations of a cover-up? This is precisely why the artificial signal scenario is so fraught with complexity. It extends beyond mere detection. It encompasses response, and response hinges on belief, which in turn depends on evidence. And in this particular instance, the evidence may be ambiguous, incomplete, and open to diverse interpretations. Interpretation, alas, is where scientific objectivity often falters. Therefore, the fundamental question remains: if a signal were detected, would you wish to be informed? Even if it could not be definitively confirmed, even if it were potentially erroneous. For while ignorance may offer comfort and certainty provides reassurance, ambiguity is profoundly unsettling, and sometimes ambiguity is the only truth we are afforded. Part 8 delves into scenarios 5 and 6, atmospheric anomaly and disclosure cascade. Let us shift our focus from the vastness of deep space to phenomena closer to home, specifically Earth's atmosphere, and even more precisely, the ionosphere. This tenuous layer, situated between altitudes of 100 and 1,000 kilometers, is where solar ultraviolet radiation ionizes atmospheric atoms, creating a plasma. This region is vital for radio communication, as it reflects certain frequencies, enabling signals to traverse distances beyond the horizon. It also plays a crucial role in GPS functionality. Satellites transmit signals through the ionosphere to ground receivers, but the ionized plasma introduces a delay in these signals, the magnitude of which is contingent upon the electron density. Consequently, GPS systems constantly monitor ionospheric conditions and apply corrections. The ionosphere is highly sensitive to solar activity. When the sun emits a flare or a coronal mass ejection, the resultant charged particles interact with Earth's magnetic field, inducing disturbances. These disturbances manifest as auroras and also cause fluctuations in electron density, leading to reduced GPS accuracy and degraded radio communications. In extreme cases, satellites can sustain damage. However, the ionosphere is susceptible to other influences as well. Meteor showers, for example, occur when Earth passes through a stream of debris. Thousands of meteors incinerate in the upper atmosphere, vaporizing and ionizing the material, creating transient layers of heightened electron density. These layers can reflect radio waves in unusual ways and cause brief disruptions in satellite signals. So the question arises, could 3I Atlas have influenced Earth's ionosphere? Not through direct impact. It was not destined to collide with our planet. Rather, through its coma, the cloud of ionized gas and dust trailing behind it. Could that cloud have intersected Earth's magnetosphere? Could it have induced a transient disturbance? The answer depends on the precise geometry. 3I Atlas achieved its closest approach to Earth in late September and early October, at a distance of approximately 1.2 astronomical units, which translates to about 180 million kilometers. This distance is too great for direct interaction. However, the coma extends far beyond the nucleus, and the ion tail propelled by the solar wind can span millions of kilometers. Could that tail have grazed Earth's magnetosphere? Could charged particles from the comet have been channeled down magnetic field lines? I lack the specific data to confirm this. I am unaware if anyone was specifically monitoring ionospheric conditions during that particular time frame. However, if they were, and if ground-based receivers or satellites detected anomalous spikes in electron density, if GPS signals exhibited unusual delays, and if any of these anomalies correlated with the comet's passage, it would indeed be noteworthy, though not conclusive. Furthermore, consider Mars. On October 3rd, 3I Atlas passed within 0.19 astronomical units of Mars, a considerably closer proximity than its approach to Earth. Mars is equipped with orbiters, rovers, and scientific instruments. Could any of these have detected atmospheric effects? Mars possesses a tenuous atmosphere, but it does have an ionosphere and experiences auroras, driven not by a global magnetic field like Earth's, but by localized magnetic crustal anomalies. If the comet's coma interacted with Mars's ionosphere, if orbiters detected transient glows or ion spikes, that would be significant. Again, I lack the specific data. Perhaps this data exists, residing in an archive, awaiting analysis by someone. Or perhaps no one was looking because, after all, 3I Atlas is merely a comet, expected to be inert and non-threatening. Consequently, instruments may not have been oriented correctly, data might not have been flagged as significant, and any anomaly, if it exists, could be concealed within the background noise. This is the frustrating nature of black swan events. One does not know where to search until after the fact, by which time the opportunity has passed, the data is archived, and public attention has shifted elsewhere. Now let us address the scenario of a disclosure cascade. This situation is less concerned with the laws of physics and more with the dissemination of information, specifically how space agencies communicate, what information is made public, and the inherent delay between observation and announcement. The International Asteroid Warning Network orchestrated an observational campaign for 3I Atlas. This is a public undertaking involving multiple telescopes and several nations sharing data. Such a coordinated effort is standard practice for objects of interest and does not inherently imply conspiracy. Rather, it signifies scientific collaboration. However, this is where the situation can become ambiguous. What if that collaboration uncovered something unexpected? What if telescopes detected an anomaly? Not necessarily a dramatic one, not necessarily definitive proof of anything, but sufficient to warrant a more thorough examination of archival data, sufficient to justify discrete meetings, and sufficient to initiate internal discussions about how to frame the findings. Imagine this. During the observational campaign, a discrepancy is noticed in spacecraft telemetry. Perhaps a Mars orbiter recorded a slight timing offset during the close approach on October 3rd. While this offset might fall within acceptable error margins, it is nonetheless present and coincides with the comet's passage. Consequently, other data sources are consulted. Telemetry from other missions is retrieved, revealing further offsets. These are minor, subtle, but correlated. Individually, none of these findings are conclusive, nor do they prove anything. However, their confluence is peculiar. Peculiar enough for a memorandum to be drafted, for a working group to be convened, and for data to be reissued with updated calibrations. And if one is attentive, if one is actively seeking patterns, such developments might be noticed. One might perceive the initial stages of a cascade unfolding. I am not asserting this definitively occurred, but rather illustrating how disclosure might manifest in the 21st century. Not through a sensational press conference or the presentation of irrefutable evidence, but rather as a gradual release of information, a series of minor revelations. Each individual revelation might be plausible and explainable on its own, but collectively they begin to form a discernible pattern. This pattern suggests that something significant was observed, something was deliberated upon, and something was deemed sufficiently important to warrant a reevaluation of existing assumptions. And here is the critical point. If such a cascade is indeed in progress, we would likely not recognize it in real time. We would only perceive it in retrospect, when someone eventually connects the disparate pieces of information. When the timeline becomes clear and the archived memos, data releases, and private workshops are synthesized into a coherent narrative, by which point the precise moment of disclosure would be impossible to pinpoint, as it was not a singular event, but rather a process. And processes remain invisible until their completion. Therefore, the pertinent question is, are we currently experiencing such a disclosure cascade? Are space agencies engaging in quiet coordination? Are archival anomalies being re-examined? Are meetings taking place behind closed doors? Perhaps, or perhaps not. However, the very fact that we cannot be certain is precisely the point. For black swan events thrive in uncertainty, residing in the liminal spaces between raw data and its interpretation, between observation and official announcement. And sometimes, by the time an announcement is finally made, the event itself has already concluded. Part 9 presents Scenarios 7 and 8, Psychological Singularity and Reality Glitch. We now venture into the most peculiar of territories, scenarios that diverge from the realm of physics and delve into the domains of perception, consciousness, and the human response to the unknown. For sometimes the impact of an event is not physical, but psychological, social, manifesting in the way belief can shape reality. Psychological singularity posits that collective attention can generate consequences irrespective of the object's intrinsic nature. Consider historical precedents. During the appearance of Halley's Comet in 1910, a segment of the population experienced panic. Newspapers published sensationalized accounts of Earth passing through the comet's tail. Entrepreneurs marketed comet pills as protection against poisonous gases. In reality, there was no danger. The comet's tail is so diffuse as to pose no threat whatsoever. However, the belief in imminent peril produced tangible social effects, widespread anxiety, irrational behavior, and disruptions in financial markets. The event acquired significance not due to its objective characteristics, but because of the human reaction to it. Alternatively, consider the Y2K bug. Computers used two-digit year designations, leading to concerns among programmers that systems would fail when the year transitioned from 99 to 00. Billions were invested in corrective measures, contingency plans were formulated, and some individuals stockpiled essential supplies. When midnight arrived, no catastrophic events materialized. Most systems functioned as intended. Nevertheless, the preparation, the pervasive fear, and the collective response themselves had real-world consequences. Resources were reallocated, careers were established, and entire industries underwent strategic shifts. So, what if 3 Atlas were to precipitate a similar phenomenon? What if speculation began to escalate? What if media coverage intensified? What if a sufficient number of individuals became convinced that something significant was imminent, not based on concrete evidence, but on the momentum of the narrative? Because the story resonated as plausible, and because humans, finding uncertainty profoundly uncomfortable, crave resolution. Imagine this scenario. Social media platforms erupt with theories. Online forums become abuzz with speculation. Hashtags trend globally. Some individuals claim to have experienced dreams related to the comet. Others report experiencing synchronicities, meaningful coincidences inexplicably tied to the date. Scientists issue statements intended to allay fears, but these statements are measured and cautious, often employing phrases like "no evidence of danger," rather than an absolute declaration of safety. This linguistic hedging, this cautious phrasing, is frequently interpreted as doubt, as a veiled admission of hidden knowledge, or as confirmation that crucial information is being withheld. Policymakers begin receiving numerous calls. Journalists initiate extensive inquiries. Congressional aides request briefings. Suddenly, space agencies find themselves compelled to respond, not because the comet poses a direct threat, but because the perception of a threat has gained considerable momentum. And that momentum, in turn, generates tangible, real-world consequences. Budgets are adjusted, telescope observation time is reallocated, and emergency protocols are reviewed. These actions are driven not by data, but by widespread belief. And here lies the recursive paradox. Once these consequences manifest, once resources are diverted, once the object becomes the focal point of international attention, it objectively acquires significance. not due to its inherent nature, but because of what we, collectively, have made it. The belief, in essence, creates the reality. The narrative becomes self-fulfilling. And years later, when historians look back, they'll assert that 3 Atlas held significance because of the cascade of events that followed. They'll point to the shifts in policy, the influx of funding, but they will overlook the fundamental cause, as its importance was not intrinsic, but rather socially engineered, a product of widespread apprehension. This was the psychological singularity, the juncture where our capacity for attention surpassed the available information, where conviction outstripped validation, and where the representation superseded the reality. The most unsettling aspect is that there's no mechanism for prevention, as any attempt to avert it necessitates communication, and communication in turn amplifies the narrative. A lack of response is misconstrued as evasion. Openness is seen as an admission of guilt. There is no winning strategy, only mitigation. Now, let's delve into the concept of a reality glitch. This is a hypothetical scenario that ventures into metaphysical territory. It proposes that 30 Atlas could unearth or even engender irregularities within the very framework of observation, affecting how we perceive time, the synchronization of our sensitive instruments, and the coherence of data streams. Modern astronomy relies on exacting temporal precision. Spacecraft transmit signals that are meticulously time-stamped. Pulsars emit regular electromagnetic pulses that function as celestial chronometers. Terrestrial atomic clocks are synchronized with GPS satellites. All these systems operate on the assumption of uniform temporal progression, that clocks tick at predictable intervals, and that the universe adheres to a consistent chronological sequence. But what if disruptions occur? What if, under specific circumstances, timekeeping systems fall out of sync? What if multiple independent instruments register minute temporal discrepancies within the same brief period? Microsecond deviations, nanosecond residuals, all aligning with the moment of 3I Atlas's closest approach to the Sun. Is this physically plausible? Perhaps. Ionized plasma can alter the propagation of signals. Charged particles can interfere with electronic components. Immense gravitational fields can induce relativistic time dilation. However, 3 Atlas is not an object of extreme nature. Its mass is insignificant, and its gravitational influence is negligible. There's no apparent means by which it could affect timekeeping on Earth or aboard spacecraft, unless there's an unobserved factor. Unless the comet's coma generates an electromagnetic milieu that subtly influences our instruments. Unless the temporal deviations are actual and quantifiable, yet fall below our detection thresholds until someone actively seeks them. Envision a scenario where a statistical analysis is performed on pulsar timing data from October of the year 2025. The objective is to identify gravitational wave signals by comparing the arrival times of pulses across various observatories. During this process, an anomaly is detected, a cluster of residuals, minor deviations from expected values, all occurring within the same week, precisely the week of the perihelion. These deviations are within the accepted margins of error. Individually, they appear insignificant, but collectively they form a discernible pattern. Alternatively, consider spacecraft telemetry logs revealing timestamp anomalies. Orbiters around Mars, probes exploring Jupiter, and ground-based receivers all record signals arriving slightly ahead of or behind schedule. Again, these anomalies fall within error margins, but are correlated and synchronized, as if some influence was affecting signal propagation throughout the solar system during that specific time frame. What would be the implications of such a phenomenon? Could it be an instrumentation error? Certainly. A calibration mistake? Absolutely. A random fluctuation that happens to coincide? Yes. Or could it indicate that our understanding of time measurement is incomplete? that environmental factors we haven't accounted for are at play, that an interstellar object traversing our local space is causing disturbances that we are currently unable to model. I am not asserting that this occurred. I am exploring the potential meaning if it did. Because if temporal anomalies were identified and linked to 3I Atlas, that would be extraordinary. Not definitive proof of artificiality, but evidence that the universe can still astonish us. Proof that our instruments, our theoretical frameworks, and our assumptions are not as robust as we presume. This, then, is the essence of a black swan event. It's not about foreseeing the unforeseeable. It's about acknowledging the existence of unpredictability. It's about recognizing the inherent fragility of systems, the greater frequency of rare occurrences than conventional theories suggest, and the irreversible consequences when they transpire. So, which of these hypothetical scenarios reflects reality, which remain conceivable, and which will be definitively dismissed by the data we are about to acquire? Because the saga of 3 Atlas is still unfolding, and the only way to ascertain whether we are experiencing a black swan event is to persist in our observation, our measurement, and our questioning until the complete picture emerges, or until it becomes irrelevant. Part 10. A pervasive enigma. What if its influence is already reshaping our comprehension? Let us step back and conduct an evaluation. We have examined 8 distinct scenarios. Some are rooted in celestial mechanics, others are purely speculative, and some border on paranoia. However, we must now organize and assess them, evaluating their likelihood, their potential ramifications, and the existence of any supporting evidence. Without a structured framework, we are merely compiling anxieties, and anxieties devoid of analysis are unproductive. Thus, imagine a straightforward table. For each scenario, we will assign a probability rating, low, medium, or high. We will gauge the potential impact on scientific understanding, on risk assessment, and on established paradigms. Furthermore, we will note any existing evidence, not conclusive proof, but mere hints, observations that do not definitively refute the scenario. Orbital domino effect, plausibility, medium. We are aware that gravitational disturbances occur. We understand that orbits are inherently chaotic over extended periods. We know that 3 Atlas passed near Mars and is projected to approach Venus and Jupiter. Potential impact, high. A delayed chain reaction could precipitate future collision risks decades hence. Evidence, currently none. However, the absence of evidence is not evidence of its absence. The timescales are extensive, and the perturbations are exceedingly subtle. Fragmentation event, plausibility, medium. Comets are known to fragment periodically. The occurrence of an anomalous fragment is not impossible. Potential impact, medium to high, contingent on the fragment's behavior. If it exhibits directed motion, that would be paradigm-altering. Evidence. No confirmed fragmentation as of the perihelion. However, subsequent observations are ongoing. Solar disruption. Plausibility. Low. There is no established mechanism by which a comet could instigate solar activity. Potential impact. High. A significant coronal mass ejection during perihelion would profoundly affect Earth's infrastructure. Evidence would necessitate an examination of solar activity logs from late October of the year 2025. If a CME occurred, the temporal correlation would be striking. If not, the scenario's credibility would diminish. Artificial signal, plausibility, very low. This hypothesis requires extraordinary assumptions. Potential impact, extreme. It would confirm the existence of extraterrestrial intelligence and necessitate a complete reevaluation of human history. Evidence. None publicly acknowledged. However, archival data may not have been exhaustively analyzed with this specific hypothesis in mind. Atmospheric anomaly. Plausibility. Low to medium, depending on whether the comet's coma intersected with Earth's or Mars' magnetosphere. Potential impact, low to medium. It would suggest unexpected particle interactions. Evidence, unknown. Would require scrutiny of ionospheric monitoring data and Mars orbiter logs from early October. Disclosure cascade, plausibility, low to medium. Coordination of information is standard practice. Concealing anomalies would necessitate deliberate withholding. Potential impact, medium. It would erode public trust in space agencies and imply the prior non-disclosure of detections. Evidence, circumstantial. The IWN campaign is public. Further investigation would be required for other data releases. Psychological singularity. Plausibility, medium. Social dynamics are inherently unpredictable. Consequences driven by belief or historical fact. Potential impact, medium. Real-world policy shifts, alterations in funding priorities, and widespread public anxiety. Evidence. Observable to some extent in media coverage and social media trends already occurring. Reality glitch, plausibility, very low. Requires unknown physics or systematic instrumentation errors. Potential impact, extreme. It would challenge fundamental assumptions regarding time measurement and signal propagation. Evidence, none. Would necessitate in-depth archival analysis of timing data from multiple independent sources. Therefore, what conclusions can be drawn from this analysis? The majority of scenarios possess a low probability of occurrence. Some present plausible mechanisms but lack corroborating evidence. A few are already subtly manifesting, such as the psychological singularity. And one or two, like the orbital domino effect and fragmentation, remain genuinely possible over extended temporal scales. However, the overarching question remains. If 3 Atlas is sufficiently ordinary, if it is merely a comet with unusual but explicable chemical properties, why does it continue to challenge the limits of our models? Why are scientists still engaged in debate regarding its behavior? Why are we entertaining even the most exotic hypotheses? Perhaps our models are not as comprehensive as we once believed. Perhaps interstellar objects represent an entirely new domain, a new set of parameters where our established assumptions falter. Perhaps the universe is subtly reminding us that normal is a statistical construct, not an immutable law of nature. And if it is indeed abnormal, if it genuinely falls outside the purview of our models, do we possess the necessary systems to detect or respond to such an event? Planetary defense networks are adept at tracking near-Earth asteroids, but they are not equipped for interstellar visitors. SETI systems are designed to detect signals, but not those originating from comets. Space agencies monitor solar activity, but they do not systematically correlate it with the passages of smaller celestial bodies. Our systems are compartmentalized, specialized, developed to address known threats rather than unforeseen surprises. Consequently, should astronomers, by default, regard interstellar visitors as potential black swans? Should every Oumuamua, every Borisov, every three-eyed Atlas be subjected to a comprehensive suite of observations, radio scans, infrared spectroscopy, radar, photometry, and trajectory monitoring for years following their perihelion passage? Such an undertaking would be financially burdensome and necessitate extensive coordination, potentially diverting resources from other research endeavors. But what is the cost of inaction? What is the cost of overlooking a crucial signal simply because we neglected to look? What is the price of disregarding a perturbation that might, over decades, escalate into a significant threat? The risk-reward equation is asymmetric. The consequence of excessive caution is financial waste. The consequence of insufficient caution is potential catastrophe. And here lies an uncomfortable truth. We may already be enveloped by such an event. The black swan might be unfolding gradually and subtly in ways we will only comprehend once it has reached its culmination. For that is the nature of these events. They do not announce themselves. They do not await confirmation. They simply occur, and we subsequently scramble to understand them. Therefore, what are the critical decision points? What measurements continue to hold significance? Post-perihelion brightness evolution. Is its luminosity diminishing as anticipated? Is there a secondary peak suggesting fragmentation? Updates on non-gravitational acceleration. Is the comet deviating from its predicted trajectory? Radio telescope follow-up. Has anyone scanned it for signals? Archival data sweeps? Are there any temporal anomalies within spacecraft telemetry logs? Ionospheric monitoring. Were there any disturbances detected during its close approaches? Each of these measurements represents a potential thread. Pulling a single thread might yield no significant outcome. However, by extracting multiple threads, a pattern may emerge. A pattern that was previously imperceptible. A pattern that fundamentally alters our understanding. And this leads us to the concluding point. Three-eyed Atlas is not the sole anomaly gracing the celestial sphere. It is not the only enigmatic phenomenon challenging our fundamental assumptions. It is not the only object prompting scientists to pose uncomfortable questions. There are others. Fast radio bursts exhibiting inexplicable characteristics, trans-Neptunian objects with peculiar orbital paths, quantum experiments revealing temporal residuals, AI-driven discoveries uncovering patterns previously overlooked by human observation. The cosmos is replete with loose threads, and perhaps, just perhaps, they are all interwoven into the same grand tapestry. Part 11. Recurring peculiarities of fast radio bursts. Let us now shift our focus away from comets and our solar system, directing our gaze outward into the vast expanse of deep space, where energetic pulses of radio waves erupt from the darkness. Fast radio bursts, or FRBs, represent one of the most profound mysteries in contemporary astrophysics, and in a peculiar fashion, they may be linked to the narrative of Three Atlas. Fast radio bursts are precisely what their name suggests, extremely brief flashes of radio emission, lasting mere milliseconds, yet astonishingly intense, detectable across billions of light years. The inaugural discovery of such a burst occurred in 2001, embedded within archival data from the Parkes telescope, though its significance was not fully recognized until 2007. Since then, hundreds, perhaps thousands, depending on the classification criteria, have been detected. The majority are singular events, flashing once and never repeating. However, a subset exhibits repetition, and these repeating bursts are particularly enigmatic. Repetition implies a persistent source, not a transient cataclysmic event like a supernova, but rather something capable of repeated emissions. Hypotheses include neutron stars, potentially magnetars with exceptionally powerful magnetic fields, or perhaps entirely unknown phenomena. Allow me to present a recent example. FRB 22108A, discovered in 2022. While it repeats, its activity is not random. It displays distinct periodicity, with bursts clustering within active windows, followed by periods of silence, and then a recurrence of clustering. This periodicity suggests rotation, possibly a neutron star with a luminous spot, where emissions are observed each time this spot aligns with our line of sight. This is the prevailing theory. However, a significant challenge arises. The bursts do not align perfectly with standard magnetar models. Their frequency structure is unusual. Some bursts exhibit a sweep from higher to lower frequencies, while others do not. The polarization rotates in ways that are difficult to elucidate, and the energy output is immense, equivalent to the sun's energy production over decades, compressed into milliseconds. We are contemplating celestial bodies the size of cities, unleashing unimaginable power. Are these phenomena natural? Almost certainly. Are they fully understood? No. And this is where the connection to Three Atlas becomes compelling, as both entities challenge our established models, push the boundaries of what we consider normal, and invite speculation about exotic physics or even artificial origins. Consider this possibility. What if 3I Atlas emitted a radio pulse during its perihelion passage? A brief, intensely powerful burst, strong enough to be detected across galactic distances, yet sufficiently potent to be captured by nearby radio telescopes if they were precisely oriented. What would be observed? A millisecond pulse, either broadband or narrowband, perhaps displaying frequency structure and polarization. Would it be identified as an FRB, or would it be dismissed as interference? The detection of FRBs is contingent upon active observation. We identify them because we are actively searching for them, utilizing sophisticated detection pipelines and continuously scanning vast areas of the sky. However, comets are not typically subjected to radio telescope scrutiny for FRB-like emissions. Why would they be? Comets are celestial bodies composed of ice and rock. They are not known to generate the magnetic fields requisite for coherent radio emission, nor do they possess the necessary energy sources. They are generally considered passive objects that reflect and scatter sunlight. But what if this assumption is flawed? What if, under specific conditions, a comet's ionized coma can produce radio emissions? What if the interaction between the solar wind and cometary plasma engenders instabilities, leading to phenomena like magnetic reconnection events and coherent radiation? These are speculative notions, but they are not beyond the realm of possibility. Plasma physics is an intricate and non-linear field, often yielding unexpected results. Alternatively, in a more provocative interpretation, what if an FRB detected in proximity to 3I Atlas was not generated by the comet itself, but was intentionally timed to coincide with its passage, serving as a signal from another source, deliberately synchronized and using the comet as a temporal marker or beacon? This is highly speculative, but its speculative nature diminishes if a correlation is discovered. The observational challenge lies in the fact that FRBs are detected by all sky monitoring instruments, such as CHIME in Canada or ASCAP in Australia. These telescopes do not target specific celestial objects. They survey large regions of the sky. Therefore, if an FRB occurred near 3I Atlas, it would be recorded in the data. However, establishing a link to the comet would require a deliberate effort to examine whether any FRBs detected in October of the year 2025 originated from the comet's apparent position in the sky. Whether such an analysis has been conducted is uncertain. It is possible, and it is also possible that it has not. But if it were performed, and if even a single FRB were found to coincide with the comet's trajectory, that would be an extraordinary finding. Not conclusive proof of anything specific, but extraordinary because it would suggest that an entire class of celestial events has eluded our detection. We might be encountering micro-scale, local FRBs, emissions that do not traverse the universe, but originate within or just beyond our solar system. Now, let us broaden our perspective and consider the impact of observational bias. We tend to discover what we are actively seeking. CHIME detects FRBs because it is specifically designed for that purpose. However, it filters out signals that deviate from the established template, signals that are too long, too short, too weak, or too strong. It is optimized for extragalactic bursts, not for localized anomalies. Therefore, what if an entire category of radio transients remains undetected? Perhaps bursts originating from comets, asteroids, or interplanetary dust clouds, emissions that occur when charged particles interact with magnetic fields in unforeseen ways. We would not observe them because we are not looking for them, and we are not looking because we assume their existence is impossible. This highlights the inherent danger of theoretical models. They dictate our expectations, and our expectations, in turn, shape what we perceive. Everything else is relegated to the category of noise, dismissed as error, or buried in archives until someone revisits the data with fresh perspectives, novel algorithms, and new hypotheses. Suddenly, what was once deemed noise transforms into a signal, and what was considered an error becomes a discovery. Therefore, my question is this. Should we begin correlating FRB detections with the passages of interstellar objects? Should we cross-reference their sky positions and timestamps? Should we meticulously search archival data for coincidental occurrences? Because if such coincidences exist, if even a faint correlation can be established, it fundamentally alters our understanding. It implies that these celestial bodies are not as inert as we currently believe. It suggests that the universe is more dynamic and interconnected than our existing models predict. And it implies that 3i Atlas might be an integral component of a larger cosmic pattern, a pattern we are only beginning to discern. Part 12. Anomalous Solar System Object Discovery. Let us now bring our focus back to our immediate cosmic neighborhood, our solar system. Because while our attention has been captivated by 3i Atlas, other peculiar phenomena have been quietly accumulating within our astronomical catalogs. These include trans-Neptunian objects exhibiting unusual orbital characteristics, near-Earth asteroids behaving in unexplained ways, and each of these discoveries raises the same fundamental question. Are these isolated curiosities, or are they pieces of a larger, yet-to-be-assembled puzzle? Allow me to introduce you to the trans-Neptunian region. This vast expanse, located beyond Neptune's orbit, approximately 30 to 50 astronomical units from the Sun, is populated by numerous icy bodies collectively known as the Kuiper Belt. Pluto is its most renowned inhabitant, but it is home to thousands, perhaps hundreds of thousands of other objects, and their orbital trajectories offer a compelling narrative. The majority of Kuiper Belt objects traverse relatively circular or mildly elliptical paths within a generally flat disk. Their orbits are stable and predictable. However, a subset deviates from this norm. Some possess orbits inclined at extreme angles. Others exhibit perihelia that bring them significantly closer to the Sun than anticipated, and some are clustered in arrangements that appear non-random. This observed clustering was the impetus for the Planet 9 hypothesis, the proposition that a massive planet, estimated to be roughly 5 to 10 times the mass of Earth, orbits in the distant solar system, far beyond Neptune. Its gravitational influence, it is theorized, shepherds these distant objects into aligned orbital paths, thereby explaining the observed clustering and orbital tilts, as well as anomalies that might otherwise be dismissed as statistical anomalies. However, Planet 9 has never been directly observed. Its existence is inferred, a spectral entity detected within the data. Some astronomers subscribe to its reality, while others contend that the clustering is an artifact of observational bias, that we detect more objects in certain regions simply because we have directed our observational efforts more intensely toward those areas. The debate continues, with each new discovery either bolstering or undermining the hypothesis. Now, allow me to provide a specific illustration. Consider a trans-Neptunian object discovered recently, which we shall designate as 2025 TN-103. Its orbital path is notably peculiar, characterized by extreme ellipticity. Its perihelion occurs at approximately 40 astronomical units, while its aphelion extends beyond 1,000 astronomical units. Its orbital period spans tens of thousands of years, and its inclination relative to the ecliptic is over 60 degrees. How did such an orbit form? Perhaps it was due to gravitational jostling by Neptune, possibly an encounter that occurred billions of years ago, flinging it far out. Or maybe it was influenced by the gravitational pull of Planet 9, or perhaps some other cosmic event, like a passing star or a rogue planet, an interaction so ancient that we can no longer precisely reconstruct it. However, here's the intriguing part. When we map the paths of these extremely distant trans-Neptunian objects, they don't move randomly. Instead, they bunch together. Their points of closest approach to the Sun, known as the arguments of perihelion, align, and their points where their orbits cross the Sun's equatorial plane, called the longitudes of ascending node, also cluster. This is highly suspicious, as random scattering should result in chaos, not such orderly alignment. This suggests that there might be something out there, something substantial and unseen, subtly guiding these orbits. Alternatively, this alignment could be an illusion, a trick of our observations, a consequence of where and when we've directed our telescopes. The jury is still out on this matter, but the very fact that we are still debating it underscores the incompleteness of our current understanding. We are uncertain about what lies beyond. We don't know what sculpted the structure of the outer solar system, and within this uncertainty lie the potential for truly unexpected phenomena. Now, let's draw a parallel to the object designated Three-Eye Atlas. Both are unusual entities. Both defy our conventional expectations. Both compel us to question what constitutes normal and what lies outside that definition. And both highlight deficiencies in our models for celestial populations. We believed we had a firm grasp on comets. We thought we understood trans-Neptunian objects. But upon closer examination, when we scrutinize the outliers, established patterns begin to break down, leading us to realize that what we perceive as normal is merely the category we have encountered and measured most frequently. So, are these peculiar objects isolated incidents, or are they indicators of a more widespread phenomenon? Could there be a population of interstellar travelers that we haven't yet detected? Objects that traverse the solar system on a regular basis, yet remain elusive due to their faintness or their speed. Is it possible that there's a collection of extreme Kuiper Belt objects shaped by interactions that we simply don't comprehend? Perhaps the solar system is inherently more disordered, more unpredictable, and more astonishing than the textbooks portray. And here's the crucial point. If these objects are part of a larger pattern, if they are linked by some underlying cosmic process, we won't recognize it until we have amassed sufficient data, until we have cataloged a substantial number of these outliers, and until someone performs a statistical analysis that reveals a correlation. By that time, the pattern will likely seem obvious, and we'll wonder why we didn't perceive it sooner. The reason we didn't see it is because we weren't actively looking for it. Our existing models led us to overlook it. This is the essence of scientific discovery. We tend to find what we are searching for and miss what we are not. The pertinent question then becomes, what are we currently overlooking? What patterns are subtly present but unseen? And will we identify them before they become critical, or will our understanding only emerge in retrospect when it's too late to take appropriate action? Part 13. Anomalies in Quantum Physics News. Let us now venture into even more peculiar realms. Fundamental physics. This is the very foundation of our comprehension, the bedrock of the constants and laws we assume to be universal, immutable, and eternal. But what if this assumption is flawed? What if the universe possesses a greater degree of fragility, mutability, and unexpectedness than we currently believe? In the year 2024, a research paper was published on the RCIV preprint server, suggesting a potential anomaly in the fine structure constant, denoted by alpha. This constant quantifies the strength of electromagnetic interactions and is integral to countless areas of physics, including atomic spectra, quantum mechanics, and electromagnetism. It is conventionally understood to be a universal constant, unchanging across the cosmos and throughout time. However, this paper analyzed quasar spectra from distant galaxies, the light from which has traveled billions of years to reach us. The analysis revealed subtle indications that alpha might have been different in the early universe, differing by mere parts per million. While this difference is minute, it is statistically significant if it proves to be a genuine effect. The physics community is currently divided on this issue. Some attribute the findings to calibration errors, while others suspect systematic biases within the data. A third faction believes the results are authentic and represent a revolutionary discovery. The debate is ongoing, and further data collection and more precise measurements are required, along with independent verification. Nevertheless, the possibility persists. The possibility that fundamental constants are not truly constant, and that the universe undergoes transformations beyond our current comprehension. Now, let's shift our attention to timing discrepancies in pulsars. Pulsars are regarded as the most precise cosmic clocks. These neutron stars rotate hundreds of times per second, emitting pulses with such regularity that they can be used to synchronize time. Astronomers employ pulsar timing arrays to detect gravitational waves by meticulously measuring the arrival times of pulses from numerous pulsars and searching for synchronized deviations. These deviations are expected to arise from the space-time ripples generated by distant black hole mergers. However, there are instances where these deviations do not correlate as expected. Occasionally, individual pulses exhibit timing residuals that defy explanation, which are typically attributed to noise, instrumental errors, or the effects of the interstellar medium. Yet, in some cases, these residuals are unusually large, persist for extended periods, or display peculiar characteristics, prompting speculation about alternative explanations. What if space-time itself is inherently more erratic than we assume? What if there are unforeseen glitches, fluctuations, or anomalies that our current models do not account for? Let us now connect this to 3i Atlas and the hypothetical reality glitch scenario. If fundamental physics exhibits imperfections, if constants are not perfectly uniform, and if timing mechanisms are less robust than we presume, could an interstellar object passing through our solar system inadvertently highlight these imperfections? Could it interact with the local fabric of space-time in a manner that exposes underlying instabilities? I am not suggesting that 3 Atlas possesses some inherent exotic property. Its mass is too small, and its gravitational influence is negligible. However, what if it is traversing a region of space-time that is already subtly anomalous? A region characterized by a higher-than-average density of dark matter, or one influenced by a passing gravitational wave. Or perhaps a region where, for reasons yet unknown, physical constants exhibit minute variations. If such conditions were true, instruments observing the comet might detect anomalies, timing offsets, spectral shifts, or trajectory deviations that do not conform to Newtonian or relativistic models. This would not be due to the comet's unusual nature, but rather because its environment is anomalous, and our current observational capabilities lack the necessary resolution to discern it. This is, admittedly, a highly speculative notion, but it is rooted in genuine questions concerning fundamental physics, questions that ongoing experiments, such as those at the Large Hadron Collider, the Dark Energy Survey, and pulsar timing arrays are actively investigating. The more precisely we measure the universe, the more we uncover anomalies, small deviations, edge cases, and outliers that deviate from the standard model. Each of these outliers represents either an error in our measurements or a genuine discovery. The challenge lies in discerning which is which, as errors are common while discoveries are rare. Distinguishing between them demands rigor, reproducibility, and independent confirmation. However, sometimes we are presented with only a single opportunity, a solitary measurement, or a unique object passing through. If we dismiss such an event as an error, we risk missing a groundbreaking discovery. Conversely, if we prematurely claim it as a discovery, we risk being incorrect. And being incorrect in science can lead to embarrassment, accusations of carelessness, and even the derailment of a scientific career. Consequently, scientists tend to err on the side of caution, demanding a high degree of confidence, multiple lines of evidence, and reproducibility. This is a necessary and commendable approach. However, it also means we are predisposed to overlooking discoveries, filtering out the truly anomalous as mere noise, and prioritizing safety over the potential for revolutionary insight. This brings us back to the central question. Are we examining 3i Atlas with the appropriate tools, the right hypotheses, and an adequate openness to surprise? Or are we attempting to fit it into existing models simply because it is comfortable? Because that is what we have been trained to do, and because admitting our lack of understanding is more difficult than pretending we possess it? I do not have definitive answers, but I do have questions. And questions are the genesis of scientific inquiry, the foundation of discovery, and the starting point for understanding. If 3 Atlas offers us any lesson, it should be this. The universe remains capable of astonishing us, and we must be prepared for it. Part 14. AI-driven breakthroughs in signal and pattern detection. Contemporary science finds itself simultaneously inundated and empowered by its own remarkable achievements. Every night, our instruments furnish us with an unprecedented volume of information, far exceeding what any previous generation could have imagined processing. Telescopes survey the cosmos, generating terabytes of data before the break of dawn. Satellites circling Earth transmit continuous streams of measurements, capturing everything from temperature fluctuations to radiation levels and magnetospheric flux. Particle accelerators record billions of collisions per second, each collision holding the potential key to unraveling the fundamental fabric of reality. Yet, despite this deluge of data, we are incapable of examining it all. We cannot scrutinize every image, verify every spectrum, or analyze every line of code that attempts to describe the universe back to us. The sheer volume of incoming information has surpassed the processing capacity of the human brain. Consequently, we resort to automation. We develop algorithms designed to sift through the noise, to highlight what we already believe to be significant. We create filters to eliminate false positives and to simplify complexity. We entrust these automated systems to identify familiar phenomena and discard the rest. But what happens when the truth lies concealed within the discarded data? What if the signal of the century, the anomaly that could redefine physics itself, has been quietly removed by our filters because it did not conform to a pre-existing pattern? This is precisely where artificial intelligence introduces a transformative element to the narrative. Machine learning operates differently from rigid instructions. It learns directly from the data. Rather than relying on inflexible filters, it adapts. It identifies patterns that elude our mathematical descriptions, perceives structures that are beyond our visualization capabilities, and notices deviations that we cannot readily rationalize. The AI does not possess preconceived notions of what it is searching for, and paradoxically, this is its greatest strength. In recent years, AI has begun to yield genuine scientific discoveries, not mere simulations or theoretical predictions, but verifiable findings. Consider the Kepler Space Telescope. Between the years 2009 and 2013, Kepler meticulously observed more than 150,000 stars, recording their brightness at intervals of a few minutes in its quest to detect transiting exoplanets. The mission's standard analysis pipeline successfully identified thousands of worlds. However, this pipeline was optimized for predictable, regular dips in stellar brightness, indicative of periodic orbits, and clear, strong signals. Yet, the universe does not always adhere to such predictable patterns. In the year 2023, a research team applied deep learning techniques to the historical Kepler data. They trained neural networks not on theoretical models, but directly on the observational data itself. The AI was not programmed with a specific definition of a planetary signature. It simply learned to discern what constituted a deviation. The outcome was the identification of several new planets that had been missed by the original algorithm. These included planets with irregular or quasi-periodic transits, likely caused by orbital perturbations from neighboring bodies or gravitational resonances. The AI even detected potential exomoons, celestial bodies that produce subtle, asymmetric dips in brightness that human-designed code had categorized as noise. This represents a quiet but profound revolution underway. AI is not replacing astronomers. Rather, it is revealing avenues of inquiry that they had not previously considered. The same pattern is observable in other scientific fields. Take, for instance, the classification of galaxies based on their morphology, spiral, elliptical, or irregular shapes. For decades, this classification process was performed manually, often relying on subjective human judgment. Subsequently, initiatives like Galaxy Zoo emerged, where volunteers worldwide categorized millions of galaxies. However, AI can now analyze tens of millions of galaxies overnight. When researchers applied AI to the Sloan Digital Sky Survey data, it began to identify galaxies that defied existing classification schemes. Some bore the hallmarks of collision remnants, while others resembled artifacts of gravitational lensing or ghost images of galaxies situated behind others. Each anomaly hinted at novel astrophysical processes. The AI was not merely replicating existing human knowledge, it was expanding the very taxonomy of the universe. Now imagine applying this same analytical approach to 3 Atlas, the interstellar object that has captured the attention of so many. It is not behaving like a typical comet. Its acceleration patterns are unusual, its tail dynamics are unpredictable, and its albedo variations do not align with standard outgassing models. What if we were to feed all the available data concerning this object into a neural network? This would include every photometric light curve, every spectroscopic reading, every trajectory log, every polarimetric profile, and every set of image metadata collected from observatories worldwide. Then we could pose a simple question to the AI. What does not fit? This approach would involve no assumptions or pre-existing models, relying solely on pattern recognition. Perhaps the AI would identify fluctuations in brightness that repeat every 6.3 hours, a regularity too precise to be coincidental, yet too erratic for simple rotation. It might detect subtle drifts in amplitude over time, suggesting a secondary periodic modulation, possibly indicative of binary rotation or an active core responding to internal thermal cycles. Or the AI could uncover something more profound, a correlation between outgassing jets and non-gravitational acceleration, but one that deviates from established physical principles. For example, the thrust vectors might be asymmetric in a manner that implies directed emission, as if something is actively steering the ejected material rather than merely venting it. While none of these findings would be conclusive on their own, they would all be highly significant. And this is precisely where discovery originates. AI possesses a singular superpower. It notices. However, it also has a critical limitation. It lacks understanding. It cannot reliably distinguish between noise and novelty, or between coincidence and causality. It flags anomalies, but it falls upon humans to determine their significance. And humans, despite our intelligence, are inherently biased. We are prone to perceive patterns where none exist, seeing faces in clouds, divine intervention in thunderstorms, and intention in random events. In science, this bias can manifest in 2 ways. We may erroneously attribute meaning where none is present, or we may dismiss a genuine phenomenon simply because it appears too extraordinary. Therefore, the solution is not to blindly trust AI. Instead, we must verify. This involves repeating the same analysis on independent data sets, employing multiple analytical models, and cross-checking results obtained from different instruments. If a signal persists, if it appears under varying conditions, and if it is detected by different algorithms with diverse underlying assumptions, only then can we begin to place credence in it. Replication serves as the antidote to illusion. Has this been done already? Has someone somewhere fed the complete dataset for 3i Atlas into a deep learning model? Perhaps a graduate student at JPL, or a hobbyist running TensorFlow on a home GPU cluster, or even a national laboratory conducting secret projects. It's possible the analysis is in progress right now, and only a small group of individuals are aware of the findings. Or, astonishingly, perhaps no one has attempted it. It's conceivable that our most significant cosmic anomaly is slipping through our grasp because no one considered allowing machines to investigate it. If this is the case, it represents a missed opportunity of immense historical proportions. This is the future of astronomy, a synergy of human intuition and machine perception, a partnership between theoretical frameworks and observational data. We construct the models, and the AI challenges them. We interpret the findings, and the AI uncovers what we could not even conceive. In the coming decade, as observatories like the Vera C. Rubin Observatory, LSST, come online, generating 20 terabytes of sky data each night, there will be no alternative. Human analysis alone will be insufficient to keep pace. The universe will necessitate algorithmic curiosity. In this new era, discovery will no longer primarily involve stumbling upon something unexpected. Instead, it will involve training machines to perceive what we have inadvertently trained ourselves to ignore. Herein lies the full circle. A black swan event in space is not merely a surprise. It is something so far removed from our expectations that our entire conceptual framework must be revised to accommodate it. But how can we detect the truly unexpected if our search is confined to what we anticipate? This is the paradox of modern science. The more advanced our instruments become, the narrower our vision may inadvertently grow as we become immersed in precision and resort to filtering, automation, and limitation. AI has the potential to be the key that unlocks this loop. Because if 3E Atlas is anything, a naturally occurring oddity, a misidentified interstellar relic, or something far more extraordinary, it represents a test of our capacity to perceive beyond our established models, to search without knowing precisely what we are looking for. And if an AI at some future point discovers something within its data, something we cannot explain, something we cannot replicate, something that challenges the very foundations of physics, that would be the ultimate black swan. A discovery not made by humans actively seeking meaning, but by a machine identifying something that human imagination could not conjure. Somewhere in a climate-controlled server room, bathed in cool white light, petabytes of sky data lie waiting, invisible to the human eye, yet brimming with secrets. An algorithm will awaken, sift through the noise, and perhaps, just perhaps, notice a flicker that no one else has perceived. A pixel slightly too bright, a curve subtly misaligned, a pattern that simply does not conform. And from this faint whisper of data, a profound question will emerge. Is this merely noise, or did the universe just subtly signal its presence? This is the era we are entering, an era where machines observe the cosmos, not merely on our behalf, but in partnership with us. And when the next anomaly akin to 3i Atlas arrives, it will not only test our scientific understanding, but also our ability to heed what the machines are attempting to communicate. Part 15, The Final Reckoning and Future Outlook. And so we find ourselves at this juncture, having delved into 15,000 words, investigating a comet that could amount to nothing or could signify everything. 3i Atlas, an interstellar visitor that graced our solar system in July 2025, exhibited outgassing when it was not expected to, displayed a chemical composition unlike anything previously observed. It passed its closest point to the Sun on October 29th and is now receding into the darkness, fading from view, and retreating back into the void from which it emerged. The central question persists. Is this merely an unusual comet, or is it a dormant black swan event, poised to unfold in unforeseen ways. Let us re-examine the various scenarios proposed. Orbital dynamics involving gravitational interactions are plausible over decadal timescales. We cannot definitively rule this out, nor can we yet confirm it. Confirmation will likely only come if some unexpected phenomenon occurs years from now. A fragmentation event is also a possibility. While no confirmed fragmentation has occurred to date, the stresses experienced at perihelion could trigger a delayed breakup. Follow-up observations are continuing. A solar disruption scenario has lost credibility, as no significant solar events coincided with the comet's perihelion. However, the underlying question remains valid for future interstellar visitors. An artificial signal scenario has not been definitively detected, though archival searches are ongoing. While improbable, the stakes are exceptionally high. An atmospheric anomaly is unclear. The necessary data exists, but analysis is still required. A disclosure cascade is a possibility, potentially subtle and invisible in real time. A psychological singularity is already manifesting, evidenced by media coverage and widespread public speculation, leading to tangible consequences stemming from perceived uncertainty. The reality glitch scenario remains without evidence and is highly speculative, though philosophically intriguing. Therefore, what remains plausible? Orbital perturbations, fragmentation, and psychological effects appear to be the most likely scenarios. What has been largely ruled out? Solar disruption. Artificial signals and reality glitches, for the most part, remain in the realm of "we haven't investigated thoroughly enough to say no." This is the frustrating aspect. The absence of evidence is not evidence of absence. Simply because we haven't detected something does not inherently mean it doesn't exist. So, what happens next? What observations are most critical? Continued monitoring of post-perihelion brightness is essential. Is the light curve decaying as predicted? Are there any secondary peaks or unusual fading rates? Updates on non-gravitational acceleration are also vital. Is the trajectory aligning with predictions, or are there deviations as outgassing continues? Further radio telescope follow-up is necessary. Have any emissions been detected, or have any archival signals been identified? Spectroscopic analysis is crucial to understand how the coma's composition is evolving. Are there any changes in the ratio of carbon dioxide to water? Fragmentation monitoring is required to determine if any new components are appearing or if unusual morphology is evident in high-resolution images. Then there is the archival work. Deep dives into existing data, AI-driven analyses, cross-correlations, and the examination of pulsar timing data, spacecraft telemetry, ionospheric logs, solar activity reports, and fast radio burst (FRB) catalogs. The goal is to identify coincidences, discern patterns, and find any potential links between 3I Atlas and broader cosmic anomalies. Some of this investigative work is underway, some is not, and some may never be pursued because no one conceived of its importance. This represents the tragedy of missed opportunities. Once the comet becomes too dim to observe, the window of opportunity closes, the collected data becomes fixed, and the archives are finalized. We are then left with only what we managed to capture, what we prioritized, and what we deemed significant at the time. However, here is the crucial point. Even if 3 Atlas is entirely ordinary, even if every peculiar observation has a common explanation, it has still imparted valuable lessons. It has reaffirmed for us that extraterrestrial visitors are a tangible reality, that their chemical composition might diverge significantly from anything within our solar system, that they challenge our established scientific frameworks, and that they compel our focused attention. Furthermore, it underscores the necessity for enhanced systems capable of both detecting and characterizing these visitors, as their continued arrival is an inevitability. Oumuamua was the inaugural instance, Boris II, 3 Atlas the third, and there will undoubtedly be more, potentially dozens each year once our detection capabilities are refined. We might observe one each month, or even one weekly. Each will be distinct, carrying unique insights into its originating star system, the conditions prevalent in interstellar space, and the vast diversity of planetary formation processes across our galaxy. Some may prove to be black swans, phenomena that defy existing classifications, shatter our current models, and necessitate a fundamental reevaluation of our assumptions. These could be artificial or intelligent in nature, or perhaps indicative of physics we have yet to comprehend. While their probability might be low, it is not zero, and a non-zero probability is precisely what defines a black swan. Therefore, what are the ramifications? If 3 Atlas represents a black swan, how will science be affected? We could witness a paradigm shift, the emergence of new physics, or a profound redefinition of our understanding of cometary behavior, interstellar objects, or something entirely unforeseen. Practically speaking, our approach to planetary defense will require reassessment. We will begin meticulously tracking interstellar visitors, invest in superior detection technologies, and foster international collaboration. Culturally, our perspective will likely shift. Space may become perceived as less predictable, less secure, more enigmatic, and consequently, a realm demanding greater caution and awe. However, if it is not a black swan, if it proves to be merely a comet, what then? We gain a measure of humility. We learn that the universe is replete with statistical outliers, that rarity does not equate to impossibility, and that strangeness does not automatically imply artificiality. We will refine our models, broaden the scope of our parameters, and become more adept at discerning anomalies from mere errors. And we will prepare for the subsequent object and the one that follows it. In either scenario, we stand to gain. In either case, we learn, for that is the inherent function of science. It is the process by which we transform uncertainty into knowledge and mystery into understanding. This transformation is not instantaneous or complete, but rather an incremental, persistent evolution over time. My concluding thought is this. If the cosmos can still present us with such surprises, if an interstellar comet can ignite such extensive speculation, analysis, wonder, and apprehension, then what else has remained concealed all this while? What other phenomena are we overlooking? What other anomalies lie dormant within our archived data? What further patterns await discovery? What additional black swans are currently circling, unseen until the precise moment of their arrival? We inhabit an era where telescopes continuously survey the entire firmament each night, where satellites provide constant monitoring of Earth, and where sophisticated experiments probe the fundamental fabric of existence. We possess an unprecedented volume of data, more advanced instruments, greater computational power, and an enhanced capacity to detect the unexpected. Yet, we remain prone to surprise, often bewildered, and frequently pose questions for which we lack immediate answers. This reality should both invigorate us and instill a sense of urgency, for it signifies that the universe has not exhausted its capacity to teach us. It implies our current models are incomplete, and that discoveries, including potential black swans capable of rewriting textbooks, shifting paradigms, and fundamentally altering our established knowledge, are on the horizon. 3 Atlas may or may not be one such event. However, the very fact of our uncertainty, the necessity of considering such a possibility, holds inherent significance. It indicates that we are finally giving serious consideration to the unpredictable nature of the universe. We are finally acknowledging that despite our constellations of satellites, telescopes, and missions, space remains largely uncharted, profoundly mysterious, and capable of delivering unforeseen shocks. If this prospect does not compel you to gaze skyward late at night, pondering the unknown, contemplating what lies ahead and reflecting on what we may have already missed, then perhaps you have not been truly attentive. The message conveyed by 3 Atlas is not one of impending doom, but rather a revelation that the cosmos is dynamic, observant, and teeming with possibilities far beyond our current imagination. Therefore, continue to observe, to question, and to wonder, for somewhere out there, another object is approaching, another anomaly awaits identification, another black swan is silently navigating the vastness of darkness. And when it finally makes its presence known, we will be left with a singular question. Did we anticipate its arrival, or did we fail to look?